Nearly all of the energy that drives Earth's variable weather and climate comes from the Sun. The Sun is just one of about 200 billion stars in the Milky Way galaxy. Compared to other stars, the Sun is considered average. However, on the scale of the solar system, it is truly gigantic. The Sun has a diameter equal to 109 Earth diameters and a volume that is 1.25 million times greater than Earth. Solar energy is not distributed evenly over Earth's surface. The amount of energy received varies with latitude, time of day, and season of the year. It is the unequal heating of Earth that ultimately creates winds and drives the surface circulation of the oceans. Movements of the atmosphere and ocean transport heat from the tropics toward the poles in an unending attempt to balance energy irregularities. The results of these processes are the phenomena we call weather. To understand how Earth's dynamic weather machine works, it is important to understand why different latitudes receive different quantities of solar energy and why we have seasons. One of Earth's principal motions is rotation, the spinning of Earth on its axis. Rotation produces the daily cycle of daylight and darkness. One rotation takes about 24 hours. A second motion of our planet is revolution, the movement of Earth in its orbit around the Sun. Earth's orbit around the Sun is not perfectly circular, but slightly elliptical. Because of this, the distance between Earth and Sun varies. Each year, on about July 4th, Earth is about 152 million kilometers from the Sun, farther than at any other time of year. This position is called aphelion. In early January, Earth is closer to the Sun than at any other point in its orbit, about 147 million kilometers. This position is called perihelion. Earth's elliptical orbit results in slightly more solar energy reaching Earth in January than in July. The small variations in solar energy received by Earth due to its elliptical orbit have a minor influence on seasonal temperatures. Consider the fact Earth is closest to the Sun during winter in the northern hemisphere. If variations in Earth-Sun distance are not the primary cause of seasonal temperature changes, what is responsible? Variations in length of daylight account for some seasonal temperature differences. Long summer days expose us to more solar radiation than short winter days. In addition to variations in length of daylight, seasonal changes in the angle of the noon sun above the horizon are an important cause of seasonal temperature changes. In summer, the noon sun is high above the horizon. As summer turns to winter, the noon sun gets lower in the sky. The closer the sun angle is to 90 degrees, the more intense the solar rays. As the angle gets lower, the solar rays become more spread out and less intense. Let's use a flashlight to illustrate. Observe how the intensity of the light beam changes when the angle of the flashlight is changed. Also, notice how the area covered by the light beam changes. From your observations, you should have concluded that when the flashlight is directly overhead, the beam is brighter and more intense, and that when the flashlight is at a lower angle, the beam is more spread out and less intense. Another factor influenced by the changing sun angle is the thickness of the atmosphere the rays must penetrate. When the sun is directly overhead, Solar rays pass through a thickness of only 1 atmosphere. Rays entering at a 30-degree angle must travel through a thickness of 2 atmospheres, whereas 5-degree angle rays pass through roughly 11 atmospheres. The longer the path through the atmosphere, the greater the chance that sunlight will be absorbed, reflected, or scattered by the atmosphere, all of which reduce solar intensity at the surface. Rays from a rising or setting sun are relatively dim because they must travel through a thickness of many atmospheres. In the preceding section, you learned that the most important reasons for seasonal variations in the amount of solar energy reaching a particular location are changes in the length of daylight and changes in the angle at which the sun's rays strike the surface. What causes these seasonal variations in sun angle and length of daylight? An important part of the answer has to do with the orientation of Earth's axis to the plane of its orbit around the Sun. This imaginary surface is called the plane of the ecliptic. Earth's axis is not perpendicular to the plane of the ecliptic, but is tilted 23.5 degrees. This tilt is called the inclination of the axis. Because the axis is tilted and always points in the same direction as Earth journeys around the Sun, the orientation of Earth's axis to the Sun's rays is constantly changing. For example, each year on June 21st or 22nd, Earth's position is such that the northern hemisphere is leaning 23.5 degrees toward the Sun. 6 months later, on December 21st or 22nd, when Earth has moved to the opposite side of its orbit, the northern hemisphere leans 23.5 degrees away from the Sun. On days between these extremes, the orientation of Earth's axis to the Sun's rays is at an angle of less than 23.5 degrees. This change in orientation causes the spot where the Sun's rays are vertical to make an annual migration from 23.5 degrees north latitude to 23.5 degrees south latitude. Historically, 4 days each year have been given special significance based on the annual migration of the direct rays of the Sun. On June 21st or 22nd, the vertical rays of the Sun are striking 23.5 degrees north latitude, a circle known on the globe as the Tropic of Cancer. For people in the Northern Hemisphere, June 21st or 22nd is known as the summer solstice, the first official day of summer. In the Southern Hemisphere, this date represents the winter solstice. 6 months later, on December 21st or 22nd, the Sun's rays are striking 23.5 degrees south latitude, a circle on the globe known as the Tropic of Capricorn. For people in the Northern Hemisphere, December 21st or 22nd is the winter solstice, the first day of winter. However, for people in the Southern Hemisphere, it is the summer solstice. The equinoxes occur in March and September, midway between the solstices. In March, the Northern Hemisphere experiences the spring equinox, whereas the September position is called the autumnal or fall equinox. In the southern hemisphere, spring begins in September and fall begins in March. During an equinox, the sun's vertical rays strike along the equator. Let's take a look at Earth from a different perspective so that we can see the circle of illumination. During an equinox, the sun's vertical rays strike the equator because Earth is in such a position in its orbit that it is tilted neither toward nor away from the sun. Grab the rotating Earth in the corner and move it to the correct location for Northern Hemisphere summer. Grab the rotating Earth in the corner and move it to the correct location for Northern Hemisphere fall. Grab the rotating Earth in the corner and move it to the correct location for Northern Hemisphere winter. Let's look more closely at the details of solstices and equinoxes. We will begin with the solstice that occurs on June 21st or 22nd. We know that the sun's vertical rays are striking the Tropic of Cancer, 23.5 degrees north latitude, and that it is the summer solstice in the northern hemisphere. Moving away from the Tropic of Cancer, the angle of the sun's noon rays gets smaller. A place located 1 degree away receives an 89-degree angle, a place 2 degrees away an 88-degree angle, and so forth. To calculate the noon-sun angle, simply find the number of degrees of latitude separating the place you want to know about from the latitude receiving the vertical rays. Then subtract that value from 90 degrees. Click on the example problem above. Let's practice this method by calculating the noon-sun angle for 55 degrees north latitude on June 21st or 22nd. Fill in the correct answers to steps 1 and 2. What if you wanted to calculate a noon-sun angle for a date other than a solstice or an equinox? How could you determine where the vertical rays of the sun were striking? Many globes have an odd-looking figure 8, called an analemma, that upon closer examination can help you solve this problem. To determine the latitude of the overhead noon sun, find the desired date on the analemma and read the coinciding latitude along the left axis. For example, on October 14th, the overhead noon sun is at 8 degrees south latitude. By knowing that the 90-degree angle rays are striking at 8 degrees south latitude on October 14th, you can calculate the noon sun angle at 40 degrees north by following the basic two-step procedure. Next, let's look at variations in length of daylight around the world on June 21st or 22nd. Notice that on June 21st or 22nd, the region within the Arctic Circle remains on the lighted side of Earth 24 hours a day. At the same time, the region surrounding the South Pole is experiencing 24 hours of darkness. The length of daylight at all Northern Hemisphere sites on June 21st or 22nd is always greater than the length of darkness. This fact can be established by comparing the fraction of a line of latitude that is on the lighted side of the globe with the fraction on the dark side. For the Northern Hemisphere, notice that the length of daylight is 12 hours at the equator and then increases as you move northward until it reaches 24 hours at the Arctic Circle. In the Southern Hemisphere, just the opposite situation prevails. Moving southward from the equator, the length of daylight gets shorter and shorter until, at the Antarctic Circle, there is 24 hours of darkness. Notice that the equator has 12 hours of daylight and 12 hours of darkness, no matter whether the Earth is experiencing a solstice or an equinox. In fact, the equator experiences 12 hours of daylight and 12 hours of darkness every day of the year. Why is this the case? To understand why the equator always has 12 hours of daylight, it is helpful to understand great circles. All great circles divide a sphere into two equal parts. All great circles divide all other great circles in half. That is, they bisect Earth. Because the circle of illumination and the equator are both great circles, half the equator is always on the lighted side of Earth, and half is always on the dark side. Therefore, the equator has 12 hours of daylight every day of the year. Now that you have reviewed the characteristics of the summer solstice in the Northern Hemisphere, can you answer these questions about the winter solstice north of the equator? Remember, the characteristics will be just opposite. Select the correct answer. Which globe represents winter in the Northern Hemisphere? What is the date of the winter solstice in the Northern Hemisphere? During the winter solstice in the Northern Hemisphere, the sun's vertical rays are striking at which latitude? During the winter solstice in the Northern Hemisphere, the area within the Arctic Circle experiences hours of daylight. Now let's turn to the equinoxes. Recall that equinoxes occur in March and September, and that the sun's vertical rays are striking the equator. Calculate the noon-sun angle for 40 degrees north latitude during an equinox. Fill in the correct answers to steps 1 and 2. What should the noon-sun angle be at 40 degrees south latitude during an equinox? During an equinox, noon-sun angles are the same at comparable latitudes in each hemisphere. Let's examine the length of daylight at different latitudes during an equinox. Notice that the circle of illumination passes directly through the poles, dividing each line of latitude in half. Because half of each latitude is on the lighted side and half is on the dark side, every location on Earth experiences 12 hours of daylight and 12 hours of darkness during an equinox. Drag the correct label to each line on the globe.